Okay, welcome to Section 3 in System Operations. The first module we're going to talk about is System Control and SCADA. And we're going to talk about some of the issues and things that go on in a power system from operating a power system perspective. Then we're going to talk about system protection and what trips transmission lines in, transformers and things. So like if you're operating a power system simulator and all of a sudden something tripped, it'll give you an idea what might have happened and what caused it. We're going to talk a little bit about telecommunications, fiber optics, microwave, power line carrier, those types of communication systems that are used in power systems to be able to connect a control center to all the real world equipment in the substations and power plants and even remote operated switches, etc. Then we're going to end up with a module on electrical safety. That's when you're going to learn about the touch and step potentials, ground potential rise, things that happen during a fault, and the ways that power companies, employees operate the system and maintain the system with the perspective of being safe at all times. Okay, so those are the 4 modules. The first one is what we're going to start, but as far as the section is concerned, the learning outcomes are describe how system control centers control the power grid through SCADA, explain the different types of protective relays and protection schemes that are used on all aspects of the power grid system, discuss the different types of telecommunication systems used in the electric power system, explain electrical safety issues in high voltage environments and at home. So those, like I said, that's going to be the wrap-up section for this course, and that will give everybody a good understanding of how power systems work, and then we will from there go into more specifics for whatever area you want to get into. Oh, forgot one. Apply concepts learned on the power system simulator, of course. Okay, Module 9, System Control and SCADA. The objectives for this module are explain the NERC interconnected system boundaries and power grids, explain the operation of interconnected power systems, discuss the basics of system stability and system recovery, explain how SCADA allows system operators to control the grid, explain the different type computer systems involved in energy management systems. Okay, here is the system control and SCADA module that shows the interconnected systems through the eyes of NERC. Now, NERC is the North American Electric Reliability Corporation, and what you're seeing here are essentially the power grids. The western states interconnection are all those states and parts of Canada, and picture all the transmission lines and all of the different power companies are all connected together, and the generators are synchronized together, the loads, everything is operating as one big massive power grid. You have the same on the eastern interconnection. Major power companies, major utilities, major load centers all connected together. All the generators spinning in harmony in order to keep frequency stable and loads and voltage stable so that loads can come and go and change and the system stays reliable. Then you have Texas, which is the interconnection there where it pretty much is a small grid system, a standalone system, just like the Quebec interconnection. So this is basically what we have in NERC, and we are operating these grids and tying to these grids in that type of manner. Okay. NERC system operators, this is in here for those of you who are interested to go on to become a certified NERC system operator. And the different types of system operators. There's reliability coordinator, there is the balancing, interchange, and transmission operator, there's transmission operator, there's balancing and interchange. And if you want to get more information on that, there's the NERC website, nerc.com. There's a study guide available if you want to look at that. I would, highly recommend anybody that wants to get into that to look at some of these. Also take some of our other online courses that are going to help you understand the concepts that are in the guidelines and also expected to know on the NERC certification exam. So this is a good fundamentals course to give everybody in all areas outside of NERC, like distribution and power plants and substation people, a good overview of the entire power system. Then from here you can go on to the branch off to the different areas like NERC or power plants or whatever you want to do, distribution. So this course is designed for a good overview, but in particular the NERC system operators, there's a little bit of reference for you if you want to pursue some additional reading. Okay, let's talk about interconnected systems. You know, we have different utilities that are all tied together with transmission lines of different voltages and transformers tying pieces together, and the grid is interconnected in a way such that the electrons are smart. They like to take the path of least resistance. So when you have a load, you're going to be getting power to that load from the nearby power plant, that system. Whether you buy power all the way across the grid and get a lower price and then you have to wheel that power, that's all about contracts and paperwork and power flows, whatever. But bottom line, the electrons are taking loops. They're taking circuit loops. They're going from your toaster to the transformer to the substation to transmission line. Okay? So the electrons are taking path of least resistance, and what the system operators are doing is trying to balance load among the transmission system so that we stay stable on voltage and stable on frequency, and power flow doesn't overload lines. If you exceed the limits on equipment, you can run into problems. So we have certain emergency measures in place to keep the system, the electrical parameters, synced up to what needs to be provided in order to have a reliable system. So we're talking about interconnected system where we're monitoring power flows and intertie conditions such that we are stable and reliable. The system works a little bit like strong rubber bands holding the different entities together. These vehicles are representing different entities or different companies, and these transmission lines and voltage points, you know, in substations, between substations, you know, you can overload a little bit and you got to come back, or you know, there might be a little bit of frequency shift and then come back. But if you shift in voltage or if you shift in frequency past a critical point, you can collapse. So we're in a condition of, you know, you can push it so far and then it'll collapse, so, or break down. And you're going to learn a lot about those in courses to come, a lot about stability and reliability well, that's it, reliability, stability, and those types of things. But just to show you that the systems are tied together with transmission lines that have resistance and capacitance and inductance, and there is some wiggle room in flow and adjustment, whatever. But if you go too far, you can trip a breaker, you can cause catastrophic equipment damage, you can have domino effect, cascading outages. So we got to know and understand what our limits are. There is some limit, but don't exceed it. Now, for example, when we're talking about a concept of balanced generation, what that means is, here we have our generator spinning with a north and south angle, a rotor angle at such a degree that it's pushing out 200 megawatts each generator. So this is a balanced condition where you have two generators at a power plant. They're both putting out 200 megawatts, and they both have the same rotor angle displacement pushing power out. If they're both the same generator size, they would have the same rotor angle. But assuming that we have the same generator size, and this is balanced, 200 megawatts each for a total of 400 megawatts, and you're going to be able to control those generators when you're on the simulator. Now here's a condition of unbalanced generation. Here we dropped down to 100 megawatts on the first generator and we upped 300 megawatts on the second generator. Notice the rotor angles changed. Again, that's for the same size generator. You will find that if we had a much larger unit putting out the 300 megawatts, we'd have a smaller rotor angle because it's capable of pushing out even more power. By the time you got up to that rotor angle, you'd be putting out quite a bit more power if it were a larger generator. But one of the important parts of these slides is to note that the rotor angle is very critical in generation output. When we watch a generator, and we watch that rotor angle and we watch its stability during a fault, what happens to that rotor angle? It could be swinging around. It's almost like timing on a car engine. In the old days we used to use a #1 spark plug and put a timing light and and watch the timing of that #1 cylinder with the spark plug and all that timing to tune up an engine. Well, that's kind of what we're doing here. We're looking at the timing of with the rotor angle, like the advance or retard of a distributor based on this rotor angle concept. So there's limitations to how far you can go to get maximum power, and then you start to reduce power. So when we're looking at the rotor angle, a system that is stable under a fault condition, all of a sudden there's a fault and the rotor angle starts bouncing around a little bit, but over time it converges back to stability again. That would be a good system. That's kind of what you want to happen. We'll get back into stable conditions. In this case, the fault did not allow the rotor angle to come back into stable conditions. It became unstable. Matter of fact, it became very unstable to a point where the rotor angle and the power out was changing, the frequency was changing so much that the protective relays had to trip the generator. Well, when you trip the generator, boy, all the loads were depending on that. Now with less generation, you now have more load than generation, so now your frequency in your system is going to start to drop. And you're going to learn all about these kinds of things when you trip a generator, what is happening. So understanding the rotor angle and the activity of how the generator is performing on the system will help you understand system stability and how the power grid remains stable even though there might be some transients going on or some power outages. You want to bring it back to stable as quickly as possible. Now here's a couple conditions on a system operations where we talk about unconditionally stable and conditionally stable. Unconditionally stable, like the one on the left, is basically the case where you really cannot fail. No matter what happens to the system, you're going to come back to stable conditions. But that's not real. What's real is conditionally stable. We have some leeway room. But if you exceed the boundaries, boy, you go unstable and your system could be going down in the dumps. So what are those limits? That's what you're going to be learning about. You're going to be learning about D curves and all kinds of different things that are going on so you can get a better handle on how to keep a system stable. And this is just from a system control point of view. Okay, this slide shows how generation loading is achieved. So in the blue curve, there's a system demand here that says, okay, over the period of a day, starting at 2 a.m. in the morning, and here's noon in the afternoon and at night, we're seeing a load come up. We're picking up the load. And in the evening, we have our maximum load and it drops off. There's a couple things that you have to keep in mind. Is that we have to have what's referred to as spinning reserve in order to have generation available in case one of the generating units were to trip. If one of the generators tripped, we have to still have gas pedal room to ramp up the other generators fast enough so that we don't have an outage or a cascading outage effect. We want, if a generator trips off, we want to ramp up the other ones because they're already spinning, they're already online, or they come up to speed very quickly and can be put online quickly. So we have what's referred to as spinning reserve so that we can handle a generator trip and absorb that with the rest of the generation and get right back to a stable frequency again. Then we have base load units. Base load units are like Unit 1 and Unit 2. They're on all the time, 24/7. Those are your nuke plants. Those are the ones that they're lowest cost steam turbines, maybe coal-fired base load units are on all the time. You got to take them down maybe once every year for a maintenance check, maybe every couple of years for a full-blown maintenance or something, that depending on the unit. Then we have, load following units where as a load comes up, you're changing the load characteristics on the generator just to kind of keep up with load. Those are load following. You have a couple of those in your system that are just keeping voltage and load maintained. And then you have what's referred to as peaking units. And in peaking units, those are the ones that only come on for peak time of the day. You need extra generation, so you turn on the peaking units. They're usually your more expensive units because you can't, otherwise you'd afford to use them all day long, all the time. More expensive, and they're designed for peaking. However, if you ran those peaking units and the load following at full capacity, for example, then you have excess capacity that you can sell in the open market. And once you start selling that power, that's a whole different animal. It's a different group of people. They're trying to sell power and make money for the company, and some companies are hurting and they need power and they have to buy it, otherwise they have, they'll have frequency issues, so they're forced to buying it. And some companies have excess capacity, a lot of hydro available, that more than their system can absorb, so they want to sell it. So there's an open market kind of competition, and that's what happens with, with load demand and also marketing. So you kind of have control and marketing, kind of two different operations in the power industry. Okay, the next slide, this one here, we're talking about generator and the generator dispatch. So the power system operator is trying to figure out where am I going to get the next, 100 megawatts when the load comes up, and a lot of evaluation factors here. There's a required total generation. The desired, what we're trying to, what do we have to consider? What does the operator or the energy management system consider when it comes to ramping up generation? It considers things like, well, what sources are available? What are the startup and shutdown and cost constraints? What if we have to start up a whole new generator just to do it? There's some cost involved with that. The incremental efficiency. Some units, the next 10 megawatts is like nothing extra. Some would be a lot extra. We've got to start up a whole new firing system or something. You've got to do something. The fuel costs. What are we doing? What's the cheapest fuel cost? What do we have ample supply of? Transmission line losses. If I start this generator instead of this one, I got to pay for the transmission line losses, the I-squared-R losses. How about high and low limit on each sources? Are we getting too close to its maximum? What about reserve and spinning reserve requirements and transmission line constraints? Boy, if I start that one up, I don't have any room for my scheduled power. Or load rate of charge, or change, the load rate of change, which how fast can I ramp up or slow down? These are factors. What are the conditions? There are many factors that go into your balancing of the generation of which ones to go into. Fortunately, there's some nice computer programs that help the system operators control this. But these are some of the things that you have to decide. If you're working on a power system simulator and you need to ramp up generation, what are going to be the factors that you pick to choose this generator versus this generator? Is it line flow? Is it losses? Is it cost? It's going to be up to you as an operator trying to figure out what's the most economical, the most reliable, and the best decisions to make. There's a lot of decisions. There's a lot of ways to skin the cat. In this case, you're going to be figuring out how all that works. Okay, a little bit more here on system demand. I'd like to point out a few things about system demand. If this happens to be the peak megawatts that were produced in your system for a whole year or any particular time frame, but let's just say a year, and this was your actual demand, okay? And this turns out to be the average demand. So this is the average demand. This is the peak demand. Just because you had a peak here, you had to have the resources to supply the peak. So what is your demand factor? It's the average divided by the peak. And if your system has a high demand factor, like this one has, then you're utilizing your energy resources very well. If you have a very poor demand factor, let's say the demand curve is way low, you're building an awful lot of power plant facilities to manage a peak that doesn't happen very long. So you want to be able to use your investment the best you can, and this is kind of a measurement of that. So you want to keep into consideration the demand curve and the resources and how we're going about operating our system. We're trying to shave the peak by energy conservation and all these other things, load curtailment, smart meters and smart grids. We're trying to shave that, energy conservation. And meanwhile, our demand's going up. If we keep going up and we don't curtail, that means we have to put new generation on. So we're trying to put renewable generation on to replace some of the old, expensive generation. We're trying to use sustainable energy, the wind and other resources, the sun. And if we can get along with those types of generation resources through curtailment and energy conservation, we don't have to add the big power plants and the coals and all those and the oil, and we can actually maintain, and that's where we're going. So just to understand demand curve and these types of things just kind of helps you understand where we are today and where we're going in the future. Okay, let's look at system disturbances. What kind of system disturbances could be seen from a system control center perspective? Well, there's frequency deviation. The supply and demand, the generation versus load. How is that balance going on? If we maintain generation with demand, with load, or supply with demand, we get a nice stable, consistent operating parameter, which we're trying to do all the time. But if there's a fault that comes in, tree gets in a line, or a transformer just explodes, or there's a car accident on a distribution, the idea here is faults happen. Lightning, galloping conductors, or all kinds of different things could be happening on the system. And how stable are we? How is the frequency behaving to it? We want to keep that frequency spot on at 60. Matter of fact, when we look at our frequency meters, we take that 60 and we really dig deep into it. So we're looking at 60.1, 60.2, or 59.9, and 59.8, and we're really trying to microscopically look at that so we can watch the frequency and be on it as soon as we can. That's frequency deviation. When it comes to cascading failures, the domino effect. Here's where you have, all right, you trip a generator. Well, now all these loads were dependent on it. So what do? If you lose generation, your grid frequency drops. So what do? Do you shed load? Yes. You shed load to be able to balance the generation and load again. Or do you bring up more generation? Yes. If I've got some spinning reserve, let's bring it on. And then you're doing everything you can to avoid cascade, and a domino effect. If you lose if you lose a load transmission line, then all of a sudden now your generation is too great. So now you're going high in frequency. So do you back off on frequency? Yes. Do you try to bring the load back on? Yes. So what are you going to do as a system operator to kind of maintain a steady condition so you don't run into cascading? Because as soon as you trip a generator, Now you got to trip loads. If you trip too many loads, now you got to trip more generation. And a lot of that stuff all happens automatically, faster than we can do it, because we can intervene, because it's all done by protective relays. So you're trying to watch all your signals, everything in the control center, the voltages, the frequencies, and all these different alarms coming in, to avoid a cascading failure. That would be the worst case. And in a total shutdown, you might as well just say good night. You want to do everything you can to avoid, those, the amount of effort to restore whatever you try to avoid. Okay. Dependency on interconnected systems. So much, you only have so much control over your own system, but you don't have much control over a neighboring system. But through the ISOs and a lot of the reliability coordinators, they're trying to watch out for everybody else's interests of everybody else. Reliability, second contingency outages, and third contingency. What's the worst case? What's the next worst scenario that can happen? And try to figure out what you can do to maintain reliability. So then you have a on uncontrollable brownout. Okay, so excuse me, that was the next one. Protection scheme failures. You can have problems with the protection scheme. You could have protective relays that inadvertently tripped. There was a condition that the 345 transmission line tripped because of a tree at one time, and then a second line tripped that looked like an overload condition, or it was basically determined to be an inadvertent trip. A second line tripped and it wasn't supposed to. So now what? We didn't even expect it to happen. It shouldn't have happened. So the protection scheme had to be fixed. Then there's voltage deviation. If the voltage isn't stable and you go into voltage control issues, you can have brownout situations where certain parts of the system is out of power, and if you don't have enough generation or equipment available to keep voltage stable, you sometimes have to curtail load or do different things that you would like to avoid. Voltage surges could happen from tripped circuit breakers, and you have transient conditions that can occur, that could affect voltage variation. Insufficient voltage support equipment, like not enough capacitors, or you have so much inductive load that you've ran out of reactive resources. So there's different areas that you want to look at to maintain voltage, maintain frequency, avoiding cascading failures. Those are some of the things that are in the minds of system control operators. And the more you can learn about it, and the more you understand how these power systems operate, the better operator you are, the better understanding you have of the power system, and the more valuable you become to a company. When it comes to emergency operations, loss of generation or loss of transmission sources, that becomes an emergency. You lose generation. Spinning reserve is you depend on. Transmission reserves, how much capacity you have left in your transmission lines. Emergency generation, what can you ramp up, turn on right away? You've got this brownout condition you want to avoid. You don't want to have rolling brownouts and rolling outages. I've been through those things. You think you have a schedule that's going to go off at 2 o'clock in your area, and it doesn't. Then you say, when's it going to happen? All of a sudden, boom, now it happened. It's not really all that controlled. Street lights are out, hospitals don't have power. It just becomes pretty chaotic. So loss of generation when you have a lot of load becomes a problem. And the same is with transmission sources. If you're importing power and you're depending on that, if something happens to that transmission line and you lose it's just like losing a generator. Same as export. You're hurting somebody else if you had to curtail your export. So these operations are very important, how you operate a power system that's so interconnected like this and so many different dependencies. So learning and understanding emergency operations is very key, and we will train you in all those aspects as we go through these courses. Here's a slide on frequency. Here's a frequency chart. I'd like you to look at a couple things here. We're starting out at 60 hertz frequency right here, and then here the frequency is going up a little bit and going negative down a little bit. And when you look at 60 hertz, trying to maintain that, and this is during a disturbance. This was the Eastern interconnection, and this is 1 minute of data. And what happened was the frequency dropped. It's going pretty crazy. It dropped even further, down even to critical limits. Down here is the minimum band. Like I was saying, we're looking at frequency microscopically, and then all of a sudden something happened here on the frequency, and all of a sudden the frequency went up. When the frequency goes up, that means maybe we shed load. Maybe over here we lost a generator, and all of a sudden the frequency is down, or a couple of generators, maybe a whole power plant if it's the whole interconnection. And then all of a sudden now we tripped load, and our frequency is very high. And then we're operating in here, and we're trying to get it back down to the green. As you can see here, it's a matter of trying to get your handle on what's going on, and let's zero back into a 60 cycle frequency with good voltage, and then get your system back. And when you start getting outages, you could have had another outage and put this way out of whack, and now you're starting the cascading, or way down here and start the cascading. You don't want that to happen. So keeping your eye on all the situation awareness alarms and whistles and bells and charts and lights, gosh, you name it, sounds, everything to kind of be aware of. That's what you're trying to digest and understand, interpolate, and try to react. And those are some of the conditions. Stable voltage, stable frequency, that's what we're trying to do. In system planning, there's a planning side of the company, and then there's the design phase, then there's the construction phase, and then there's the operation phase, and then there's the maintenance phase. So planning is pretty much up front. A lot of companies have 15, 20-year plans. They look way out into the future, have all kinds of load growth assumptions, and watch and see what transmission lines they need or power plants they need, and plan a lot of these things out. They depend heavily on load forecast accuracy, what the current generation is and import capabilities might be down the road. Resource planning, how do we know what resources are available? And transmission and distribution planning. If the distribution is where we're getting all the loads, so we want to make sure we have transmission lines there. And demand side planning. Demand side of the meter, the load, being able to control load or help conserve energy on the load side. That's the demand side. What's going on that activity? That affects load forecasting. Evaluation of alternatives, looking at all the options. What's the best thing to do here? What's the most cost effective? Long term. By the time you figure out this is the transmission line we need, now you got the public affecting you. Now you got to look back at your other alternatives. There's a lot. It takes a long time to get all the permits and those things. You're looking years in advance on the planning side. I was a transmission planning engineer for a while, and what it takes with the joint ventures and the studies with different utilities, it takes a lot of coordination, a lot of planning to figure out what is best. And then you present a resource plan, and it gets budgeted, and what happens is you take like a 20-year plan, and then you have a 10-year plan, and maybe a 3-year plan, and then a 1-year plan, and they're all tied together. So as you're moving through time, some of this, you're detailing out the 5-year plan, and you're looking further out into the future for the long-term plan, and you're trying to just kind of keep that machine going because it takes so long to build a power plant, so long to get a right-of-ways for a transmission line. You can't just, as an operator, let's say, fix things overnight. It's all about planning, and that's all. If you like looking into the future and figuring out what's best, that's system planning perspective of the power industry. Okay, on demand side planning, we talked a little bit about this. This is basically looking at what can we do to help reduce loads on the demand side of the meter. You know, we're looking at different energy programs, or maybe there's customer generation, maybe taking some of the emergency generators and putting them online even, or renewable energy options. What can we do to kind of help reduce demand? You know, if we did a really good job at reducing demand, you wouldn't need power companies, right? So the idea is there's only so much we're going to be able to do. Cogeneration, where, you know, you might be able to use, you know, some kind of a gas generator to produce power that the power company might use, and it's customer owned. There's a lot of different things that get looked into when it comes to demand side planning. Okay, next area is resource planning. And again, here's where you're looking at all the different options you have. You're looking 20 years out in the future. You're trying to figure out what are you going to do to get power into your system if your load continues to grow. And then there's all the aspects that go along with that, including, you know, environmental issues, and that could be, you know, that could stop you right in your tracks. So there's, you know, you got to keep pursuing options and figuring out when you get finally down to the end degree, the last level of detail, you have no other option, no other choice. You just have to go along with it. That's kind of when you've done all your research. Okay, we're going to change gears a little bit, talk about SCADA. SCADA is supervisory control and data acquisition. It's the system that involves a main computer at a control center and small remote computers at substations and power plants, and then you involve telecommunication facilities to connect the two together so that a control center is operating remotely the substation, opening, closing breakers, reading, monitoring, and bringing in information from CTs and PTs telling you currents and voltages and power flows and different pieces of information to help you control the power grid. So you have this control center, and you have a main computer. That's kind of like the master station. And then through communications to a substation, you have RTUs, remote terminal units, that are connecting to the protective relays so that you can open and close breakers. You can get alarms in that a breaker is now open. Uh-oh, what do I do? You know, and you have measuring devices that are telling you the analog readings of bus voltage and transformer loading. And all that information is then displayed on the computer. And it's pretty accurate. If you have some information missing, then the state estimator is trying to work on adding information, calculating information, trying to do its best in providing information. So if you lose a telecommunications line, you might be on estimated numbers. But you have to get that communication line fixed, and on the reliability side of the telecommunications line, it's got to be battery operated. It cannot go out when the AC goes out, all those kinds of things. It's just all about reliability. So SCADA is the control system used to control the system, and then the energy management system uses SCADA to get its job done. It's the one that's ramping up the most cost-effective generator, or changing generation dispatch for most reliability when it comes to single contingency and double contingency and those things. A lot of that stuff, it all gets analyzed and controlled and operated through SCADA. So if it weren't for SCADA, we couldn't do all the things we're talking about. When it comes to smart grid, that's an elaborated SCADA system where we're getting more information and doing more with it, more remote control, even having programmable logic controllers involved and automatic transfer switches. All of this is all done by communications and a form of SCADA. Okay, so that's an overview of SCADA. Okay, here's a drawing that shows in a control center where you have a map board and you have consoles and you're operating your power grid system, and hopefully there's some geographic resemblance of your system on the map board. Those consoles are operated through the main computer, and the computer is connected to a communications equipment room where you're connecting out to all the different substations, either through fiber optics, microwave, radio, copper, power line carrier. You know, there's all these different means to make communications to all the remote sites, and every one of them has to be reliable, dependable, and that's mainly it, reliable, dependable, so that you can operate the system control center properly. Now, the energy management system that's tied into SCADA has a lot of bells and whistles. And just because we have SCADA, we can do so much. I'm just going to mention a few of the boxes over here. Okay, so we have a SCADA system, you know, that's driving all this, and we have a map board and displays. All right, so in the system status processor, we have the state estimator, which is actually helping us with values and numbers. We can go into all kinds of areas where we can study the power flow and see if you know, if we have any overload conditions going on, or what could happen, what's the worst case. Look ahead contingency analysis. If a line went out, what do we do next? So what's the worst contingency? Which is the worst line that could go out right now? What are our remedial actions that we can take? You know, the energy management system fault calculation, so it calculates fault currents, you know, if something were to happen. Voltage security assessment, the stability of voltage. You know, if you go through so many of these, reactive power scheduling, you know, and then continue on here with, you know, contingency selection and analysis, real-time optimal power flows, real-time contingency and constrained optimal power flows. I mean, when you look at the different programs and operations and events going on in the background to help an operator, if a transmission crew calls up and said, "Hey, system control, I need to take this transmission line out of service for maintenance. It's got shot up insulators and I don't know how long it's going to last." And the system control operator can actually, you know, on a simulator basis, take that line out, see what kind of conditions, what the worst case contingency would be after that, to figure out what's going on. Does it look like it's okay to take that line out right now, or should we wait? And then he can make a decision to go back to that transmission crew out there and say, yes, it's okay to go ahead and take that line out. It will do that in such and such hour or whatever, and they take the line out, they can do the maintenance. Meanwhile, they're finding out that right now, boy, with that line out, this is the next worst contingency. If that happens, now we better start unloading that line a little bit, because if that goes to overload because of this line trip, we're in trouble. So you have this analysis that's going on. Well, you get to do those kinds of things on a simulator. Now, the simulator that we're going to introduce to you in this first class here is not going to be all that sophisticated in all those types of analysis. That's something that you learn as we grow in these courses. But you're going to get you're going to become familiar with the simulator. You're going to see, you're going to operate it, you're going to play around with it and get familiar with it. Then we'll get into more sophisticated scenarios. But just want you to know that all of this ties into the real world and the simulated world and with this theory. And we're hoping here to bring you up to a level of competence so you can move on in your career in this industry. Okay, preventing grid failures. Here's a good one. You're a system control operator now, and you're going to be, you know, you got a normal state going on and everything's going fine. Then all of a sudden, you know, you get an alert, you go, oh, that's not a big deal, I'll go back to normal. I can just, you know, we'll just put some more oil in that transformer tomorrow. It goes back. But all of a sudden it's alert. It's an alert that ends up becoming, you know, an extreme emergency. Are you going to be able to restore? Or is that alert saying, okay, we're just going to get off of economic dispatch and just get right back into it once we fix things? Is it something that we can control? Is it such an emergency that it just becomes extreme to us? You know, if we can't fix it, our system's going down. Okay, in this system here, we might be able to fix it, and we're still getting back into, we're trying to get back to that normal state. So we're in this state of flux. How severe is it? What do we have to do to avoid it getting worse? These are some of the conditions. What alarms are coming in? You know, how do I analyze this? What does it mean? You know, ask your coworkers. Get on the phone and talk to on the interchange and talk to somebody at the other at another utility. What is it we got to do to kind of get back to normal? You know, it's great when everything is normal. So sometimes that's when the work becomes interesting. So we're trying to get back to a normal state. So we're doing everything we can to prevent failures. And then there are failures. Now this here is looks like a 500 kV single phase transformer that failed. There are 3 of them there. One of them failed. And this is something that may have been prevented, maybe not. You know, you go back and figure it out. But meanwhile, it happened, and you're on shift, and that 500 kV line just tripped. So what are you going to do? That line's tripped. You're going to be responsible for informing operations people that can go back out to that substation, go check it out, get another spare in there, get everything going back to normal as soon as you can. Meanwhile, you're going to go back to your computer, you're going to figure out, you know, what's the next worst contingency? What do we have to do to kind of to minimize worst case scenarios? Don't want that cascaded, that domino effect to occur. So there could be problems with equipment, there could be problems with transmission lines. It's hard to say, but something that size could cause a lot of attention. A small distribution transformer failure is going to be handled by the distribution people. It's not going to be cascading effects. It might be, you know, customers out of service, you want to get them back, but something like this could be very major, very critical. Here's a case where we had ice loading on a 500 kV line. There happens to be 2 transmission lines running down the same corridor. They got iced up, and one had so much ice that it collapsed. Well, when that collapsed, it, I guess fortunately, put more load on the other line, in which the I²R losses melted the ice. So, you know, icing can happen. My experience, I did come across a 345 kV double ACSR circuit that iced up so bad that the line sagged all the way and touched the ground. Now, how it didn't collapse the towers like this one did is who knows. But it did, and the line held for 40 minutes, then it would trip again. It would run, you know, it was actually using snow as the insulation. And finally we went out there and saw that, you know, what the problem was for the line tripping, and ended up having to put more power flow through the line to get the I²R losses up, to get the heating on the conductors, melted the ice and raised the conductors back up. So this kind of stuff does happen, and it's just a matter of trying to think of all possibilities and trying to have sensors and people and maintenance, everything you can think of to avoid issues. So this is all part of power system operations. Try to avoid these kinds of failures. Okay, so in summary of this module on system control and SCADA, we talked about NERC interconnection systems, the boundaries and the power grids. Remember the eastern connection and the western interconnection? Explain the operation of interconnected power systems, how we depend on each other for power flow and generation and stability. We discussed the basics of system stability and system recovery. We explained how SCADA allows system operators to control the power grid. We explained the different computer systems involved in energy management systems. And that completes the module on system control and SCADA.